Hello everybody, today I am going to talk about interference due to transmitted light rays in thin film. In the last class I have discussed about interference due to reflected light in thin films. So today we will be dealing with transmitted light rays. Okay, so let's see how we can get the interference due to the transmitted light rays, and we will try to get the equation, the conditions to have a bright fringe and to have a dark fringe due to the transmitted light rays in thin film. So let's get started. I have a thin film. Here's my thin film having thickness T, and this material of the thin film having some refractive index mu. I'm having some monochromatic light source is falling on my thin film with some angle of incidence I. So here's my normal, this is my angle of incidence I. So in this lecture I won't be discussing all the basic stuff which I have already discussed in the last video. So I won't be telling you that the ray will bend towards the normal or away from the normal, like those things and Snell's law. Okay, here I will be just focusing on the conditions, how to get the conditions and the final result. What is the difference between the interference due to the reflected lights and interference due to the transmitted light? Are they exactly same or any kind of difference is there? We will be focusing on those things. Okay, so I won't be repeating those stuff, the basic stuff here. So again, you see, here you will, the part of this incident light ray will get reflected, but I'm not interested in that part, so I won't be drawing. Directly I will be focusing on the transmitted part. So the part of this light ray which got transmitted inside the thin film, here it is, with some angle of refraction r, and again this ray due to the bottom surface of a thin film will undergo reflection. Part of it will reflect and part of this ray will come out of the thin film. So here's the normal. So the ray which is coming out is this is the ray, the transmitted ray which is coming out of the thin film. The same phenomena, the same transmission and reflection will happen at this point. Here also the reflected ray will come, the reflected ray, and part of this reflected ray from the bottom surface will again suffer a reflection from the top surface of the thin film. And again same, due to this bottom surface, the part of this light ray will reflect and the part of this light ray will get transmit, will come out of the thin film. So here's I have the one transmitted ray, here's I have the other transmitted ray. So similar phenomena will undergo likewise. So I will be focusing on this particular two rays and I will be deriving, I will be trying to get the path difference between these two rays, and that path difference I will be equating to the constructive interference condition and destructive interference condition. So for that purpose I have to find out what is the path difference between these two light rays. How do you know that you are going to get interference due to these two light rays? Yeah, exactly. They should be coherent, then only you can have the interference pattern. Let's see whether they are having the coherence or not. See, these two light rays are coming from a single source. There is only a single monochromatic source from which these light rays are coming. So it is sure that these two light rays will have the same frequency, the same wavelength, and they will have some constant phase difference between them. But there is a difference. What is that? They won't be having exactly equal amplitude. The amplitude will be different as comparatively. The amplitude won't be equal, and I'll come back to that in a minute. And the what what if the amplitudes are not equal, what kind of changes we see in the interference pattern? I'll come back to that in a minute. So now to find out the path difference between these two light rays, I will do some geometrical okay. So I'm giving the namings. So here's my A point, and this point is B. This is C. This is D. This is E, F, and I'm drawing a perpendicular like this. I'm elongating this line. This point I'm calling it as G, and this light ray, the transmitted light ray 1, I'm drawing a perpendicular to it, and I'm calling this point as H. Okay, so because this is my refracted angle R, this will also be R. How come? Because these two normals are exactly parallel with each other. That's why this is also gonna be R. And from the incident to the refracted angle, reflection angle, angle of incidence is equals to the angle of reflection. The same principle applies here also. This is R, so this will also be R. So again, if this is R, this will also be R, and this is also R. Now, this light ray, the transmitted light ray which is coming out of the thin film, is having angle I, the angle of incidence, and this will also be that only. This is the angle of incidence I only, and this we know that this total is 90. So this is 90 minus I, and this is again I. So what this can be? It will be I. This angle is I. So now let's find out the path difference between these two light rays. The optical path difference. The optical path difference is the distance. You see, this transmitted light ray is traveling this much distance, and the other ray 2, transmitted ray 2, is traveling a bit longer distance. So till this point, if we find out, there is no path difference after these 2 points. They will travel the equal distance. Okay, but the thing is, the story is all about this region. In this region, the ray 1 is traveled this much shorter distance, but the ray 2 is traveling this plus this. So what I have to do, I have to add these lengths, and I have to subtract from these lengths. I will get the path difference between these two light rays. So the path, so this path BC plus CD is the distance traveled by the light in the medium whose refractive index is mu, minus the distance traveled by the light. This much is the distance, that is BH. In which medium that light has traveled, whose refractive index? This is the air. So its refractive index, we take it as 1. Now, from this figure, this is the R, this is also R. So both are having the same angle, and these two light rays, this is exactly parallel planes. Like this is a constant thickness thin film, so that's how this length will be equal to this length. In other words, BC is equal to CD. If that is the case, I can write 2BC mu minus BH. I have to find out, so this is the path difference, I have to find out the value of BC and BH. So from triangle BCG cos R is equals to the adjacent by hypotenuse. What is the adjacent? That is CG divided by the hypotenuse BC. So I have to find out the BC. Take it one side. BC is equals to CG. CG is same as the thickness of a thin film. So instead of CG, I can write T. So it is T by cos R. Let this be equation 1 and this be equation 2. Now I have to find out the value of BH. So before going to find out the BH, I want to do some simplification. So you see BD, this length, BG is equal to GD. BG is equals to GD. We can see from the geometry, the distance BG is exactly equal to the distance GD. That implies the distance BD can be written as 2 times the distance of GB. Okay, now from triangle PCG, tan R can be written as tan R. From this triangle BCG, tan R can be written as opposite, that is BG, divided by adjacent, that is CG. So CG. Now we have to find out the value of BG. So BG is equals to CG. What is that? CG is the length, is the thickness of a thin film, that is T into tan R. So this is my equation 3, this is my equation 4. Now what I'm going to do is I'm going to substitute the value of BG in here in equation 3. What will I get? I'll get BD is equals to 2 times of the value of BG. What is BG? BG is T tan R. T tan R. Now we will find out the value, the distance BH. The BH from this triangle, from triangle BHD, from this triangle we can find out the value, the distance BH. So from this triangle, sine I is equals to opposite. Opposite is BH divided by hypotenuse. Hypotenuse is BG, not BG, BD. The hypotenuse is BD. Now sine I is equals to the value of BH that we want to find out. So I'll take it in one side. BH is equals to BD sine I. So we know the value of BD. We have it here. This is the value of BD. I'll substitute in here. So the BD is equals to 2T tan R sine I. And we know from the Snell's law, sine I n1, the refractive index, is equals to n2 sine R. The refractive index of air is 1, so that's how this equation will become sine I by sine R is equals to mu. So you can write it as sine I is equals to mu sine R. So this BH distance will become now 2T tan R. Instead of sine I will replace that sine I with mu sine R. So let this be equation number 5. So now I will be substituting equation 2 and 5 in 1. This is the path difference. 2 times of BC. What is BC? BC is T by cos R. What remains is mu minus BH. The BH is this 2T mu tan R can be written as sin R by cos R. So I have one more sin R, so I can write it as sin square. Now I'll take common 2 mu T cos R. 1 minus, there will be nothing after taking common, 1 will be there, 2T is gone. What remains is sin square R. So 1 minus sin square R can be written as cos square R. 2T mu cos R cos square R. Cos square R, cos R will get cancelled. The path difference between two transmitted light rays from thin film is 2T mu cos R. So this is the same as that of the path, optical path difference of the reflected light rays. But when it comes to finding the true path difference for the reflected light rays, we got one additional factor for the path difference, that is due to the reflection. Due to the denser medium, the light ray was getting a path difference of lambda by 2 and the phase difference of pi. But here the reflections are happening, but those reflections are not due to the denser medium. Here the reflections are there, but those reflections are due to the rarer medium. So that's why the path difference of lambda by 2 or the phase difference pi won't come into picture of transmitted light rays. You see the reflection from this surface, yes, this is the denser and this is the rarer. So the reflection is happening due to the rarer medium, so that path difference of lambda by 2 won't come. Similarly, the reflection from here, this is the rarer medium and this is the denser medium. Same thing, the reflection is happening but due to the rarer medium. So that's why the path difference of lambda by 2 won't come into picture. This is the path difference, the final path difference for the transmitted light rays. Now we will find out the conditions to have a bright and dark fringe in transmitted light rays. So for the condition for constructive interference, the path difference should be n lambda, where n can take values from 0, 1, 2, 3 likewise. So if this is the case, we can get a constructive interference. The difference should be some integer number, either lambda, 2 lambda, 0 lambda, then only we can have a constructive interference. If I equate this path difference to the path difference which I got in the transmitted light rays, I'll be getting the condition for a bright fringe. So this is 2t mu cos r is equals to n lambda. This is the condition to have a constructive interference in thin films due to the reflected light rays. Similarly, we can find out the condition for destructive interference, that is, the path difference will be n plus half into lambda. So if I equate it to this path difference, I'll be getting 2t mu cos r is equals to n plus half lambda. So this is the path difference condition for transmitted light rays to get destructive interference. So now I will tell you what is the difference between the transmitted light rays interference and reflected light rays interference. So the interference which we get due to the reflected light rays will be a bit. So the interference due to transmitted light rays won't be that much sharp or distinct. Why? Because the amplitude difference will be more in these two light rays. The amplitude difference is more, that's why you won't get the sharp, the distinct interference pattern due to the transmitted light rays. But when it comes to the reflected light rays, we are getting sharp and distinguishable interference pattern. Why? Because the amplitude difference is less in between these transmitted light rays. That's why we will get a sharp interference in here, but here the sharpness won't be there. There is one more noticeable and most interesting fact about the interference due to transmitted and reflected light rays is that, suppose due to these transmitted light rays, if you are getting for a particular path difference, if you are getting destructive interference in here, so at that particular path difference, the remarkable thing is happening. You see, at that particular path difference in the transmitted light rays, if here you are getting a dark fringe for that particular path difference, here you will get, due to the transmitted ray, which the interference due to the transmitted rays, here you will be getting a bright fringe for that particular path difference. Why I am saying that? Because this condition is for destructive interference in the reflected interference, and this condition is for the constructive interference in the reflected light rays. That's why the conditions got flipped here. We will see the exact opposite patterns in here. Wherever you are getting a dark, here at that particular positions you will be getting bright. Wherever you are getting dark in here, at that particular path difference, you will be getting bright there. So that is the main difference in here. In the next classes, we will be talking about the films whose thickness is not constant, the thickness will vary. So thank you so much. That's it for today.